Welcome to the deep dive. If you're like most people, you are just bombarded every single day with reports and charts and metrics, all of them designed to influence you.
hmm It's a lot of noise.
It is. It's easy to feel like you're drowning. But there's this really powerful quote from the statistician W. Edwards Deming that I think just cuts right through all of it. He said, "Without data, you're just another person with an opinion."
And that's really the core of it, isn't it? Moving beyond opinion.
Exactly. So our mission today is to equip you with that foundational toolkit. We're diving into the fundamentals of statistics, the science of, collecting, analyzing, and interpreting data to make sure you're actually well informed.
And we're not just going to read definitions from a textbook. The goal here is to really understand the scaffolding that's underneath every big business decision. We have to grasp how data is structured, and maybe more importantly, how different statistical methods apply to real messy problems.
Okay, so let's unpack that with the why first.
Yeah.
For anyone listening, why is this stuff so critical? I mean, where does this science actually show up in business?
Now, it's basically the backbone of organizational control and foresight. Let's take three big areas. In accounting, for instance, statistics is like an internal diagnostic tool.
Okay.
Managers are constantly using it to compare actual financial performance, say how much they spent on materials, against what was actually budgeted. That comparison instantly flags any inefficiencies or unexpected costs.
So accounting is sort of using stats to look backward, to diagnose what went right or wrong.
Exactly. Economics, on the other hand, uses it to look at the big picture, the macro trends. They apply statistical methods to these massive data sets and analyze nationwide trends, things like employment figures, wage distributions, that kind of thing.
Which helps a business forecast what's coming down the road.
Right, years down the road. And then you have finance.
And I know finance just lives and dies by these methods.
Completely. In finance, statistics isn't, optional, it's the product. Risk analysts use probability models all day long to assess the likelihood of something happening, like a loan default. And that assessment is absolutely critical for pricing financial instruments. If you miscalculate that probability, the whole business model just collapses. It turns risk from a gut feeling into actual measurable math.
That's powerful context. So if all these high-stakes decisions rely on data, we have to start at the absolute ground level. What are the fundamental building blocks we're even looking at?
Think of it like a building. It's made from three fundamental blocks. First, you have the elements.
The elements.
These are the entities, the subjects that you're collecting data on. So if you're studying sales, an element could be a single customer or a specific product or maybe one retail store.
So the element is kind of the container for all the information?
Precisely. The next block is the variable. A variable is a characteristic of interest that you measure on that element. So if your element is a retail store, the variables might be its square footage, its daily foot traffic, or maybe its annual revenue.
And if I put those two together, the square footage, the foot traffic, the revenue for one specific store, that whole package is the observation for that store. Am I getting that right?
That's the structure.
Exactly.
The observation is the complete set of measurements for one particular element. And this leads to a really critical rule. You study, say, 200 elements, 200 customers, you will have 200 observations. Okay, that makes sense. And if you measure 4 variables for each of those customers, your data set has 800 total data values. Understanding that structure is key, so you don't get lost in just a sea of numbers. All right, so now that we have the structure, we can get into what I think is maybe the most crucial part of this whole deep dive, the type of data. Because the type determines the rules of the road. It dictates what math you're even allowed to do. The scales of measurement, yes. This is where so many people and businesses make fundamental mistakes. We basically divide data into two main camps, categorical and quantitative.
Okay.
Let's start with categorical data, or qualitative data. These are just labels or names used to identify an attribute. And the kind of statistical analysis you can do is pretty limited because you can't really do standard arithmetic on them.
Right.
Now, within categorical, you have nominal and ordinal. Nominal categories have no inherent order. Think vehicle type, sedan, SUV, truck, or nationality. You can count how many you have, but you can't say an SUV is more than a sedan in a mathematical sense.
But then we have ordinal, where the order does matter. This is the rank.
It does, and this is where the mistakes happen. Ordinal data has a meaningful order, like a satisfaction level survey. Satisfied, neutral, dissatisfied, or maybe education level. We know a graduate degree is higher than a high school diploma.
But the difference between those ranks isn't a consistent, quantifiable distance.
Exactly. And that's the trap.
Wait, let me just pause on that. If ordinal data has a rank, why can't I average it? A rank of 3 is definitely better than a rank of 1. If I assign numbers 1 to 5 for satisfaction, why can't I just calculate the mean score?
Because those numbers 1 to 5 are just proxies for labels. The scale underneath them doesn't have a consistent equal difference between the intervals. So if you average excellent, good, and fair, and you get, say, 2.3, what does 2.3 even mean? It's a meaningless point on an arithmetic scale.
Oh, I see.
Companies do this all the time. They treat customer satisfaction surveys like their ratio data, and they try to calculate this average distance between ranks, but it's just mathematically unsound. That is a massive takeaway right there. Just because it has a number attached doesn't mean you can average it. So let's contrast that with the second major camp, quantitative data.
Right.
Quantitative data is numeric. It tells you how many which is discrete or how much which is continuous. And here, standard arithmetic operations are totally meaningful.
So discrete is countable.
Yeah, countable. You can't have fractions, the number of transactions or the number of employees in a department. Continuous data, on the other hand, measures how much, and it can be any value in a range.
Yeah.
Product weight, distance traveled, temperature. You can have a weight of 10.1 pounds or 10.11 or 10.111 and so on.
And even inside this powerful quantitative camp, there's one last critical distinction, right? Interval versus ratio. And it all comes down to the concept of zero.
It's all about having a true 0 point. Interval data has meaningful differences between values, but no true 0. 0 doesn't mean the absence of the thing. Temperature in Celsius or Fahrenheit is the classic example. 0 degrees is just a point on the scale. It doesn't mean there's no thermal energy.
So you can't say 40 degrees is twice as hot as 20 degrees.
You can't. Exactly. But with ratio data, that's your standard business yardstick.
It has meaningful differences and a true 0 point. 0 truly means nothing is there. This is what you need for most business metrics. Height, weight, sales figures, revenue. If your revenue is 0, you literally earned nothing. That allows you to make ratio statements like, this quarter's sales were double last quarter's. Okay, so knowing those data types lets us talk about what we actually do with the information. If the type dictates the math, the overall goal must dictate the method. Are we just summing things up, or are we trying to predict the future?
And that's the perfect way to frame the difference between descriptive statistics and inferential statistics. Descriptive statistics are just summaries. They're tabular, graphical, numerical summaries of data you've already collected. You're just describing the past.
Like the mean, the average, that's a core descriptive statistic.
It is. In that Hudson Auto Repair study, for instance, the manager looked at 50 customer invoices for tune-ups.
Right, to understand the cost of parts.
That's purely descriptive. Based on those 50 tune-ups, he calculated that the mean cost of parts was $79. He also saw that the most frequent cost range, between $70 and $79, had 16 invoices, which was 32% of that sample.
And this is the key, those conclusions only apply to those 50 invoices.
That's the key. Now, what if the manager wants to predict the costs for the next 50 customers, or all customers next year?
Now we're in a totally different world. Now we're in the realm of inferential statistics.
Precisely. Inferential statistics is the process of using data from a manageable sample, those 50 invoices, to make estimates or draw conclusions about the much larger population, which would be all tune-up customers, past, present, and future. This is where you get estimation, hypothesis testing, prediction.
And to do that kind of prediction well, we have to know how the data was collected in the first place. That brings us to study design.
Right. There are two main ways. First is observational studies. Here, we make no attempt to control or influence the variables. Think of a market survey, or, as the sources mention, researchers watching customers in a Walmart to record gender, time spent, and amount spent. They're just recording what naturally exists.
Just watching.
Just watching. The second, which is much more complex, is experimental studies. Here, we actively identify variables and we control their values to see how they influence an outcome. This is the gold standard for certainty.
Like a drug trial.
It's exactly. The 1954 Public Health Service experiment for the Salk polio vaccine is a historic example. They selected nearly 2 million children and controlled who got the vaccine and who got the placebo. A massive controlled experiment.
That level of rigor is obviously essential for certainty, but it's often impossible in the real business world. And that need for fast, accurate prediction, that's what connects all these fundamentals to the huge computational fields that define modern business today, the 21st century toolkit.
Absolutely. The modern world is all about the velocity and volume of data, and that scale requires these new fields, but all of them rely directly on the descriptive and inferential statistics we just covered. So let's start with the big one, Data science. Data science is really the broad interdisciplinary field. It's the umbrella term for the whole operation of extracting knowledge and insights from data, both structured and unstructured.
And the core application of that today would be what?
Oh, personalization and optimization. We use data science models, which are often predictive, to personalize marketing by forecasting what you might buy next, or to optimize these huge supply chains by predicting demand fluctuations months in advance.
Which requires an insane amount of information processing. That brings us to big data. This is just about the sheer scale of it all.
Yeah, big data refers to those extremely large data sets. We talk about their volume, velocity, and variety. They require massive computational power to find patterns, especially in human behavior. Financial institutions use it to monitor millions of transactions an hour to spot fraud patterns almost instantly.
Wow.
Or think about Amazon. They use the velocity of big data to adjust product prices constantly, sometimes every 15 minutes, based on what competitors are doing and what current demand looks like.
And then we have data mining, which sounds like we're sifting through all that big data to find the gold nuggets.
That's a perfect analogy. Data mining is the practice of examining those large databases, the big data, to generate new information. It's essentially inferential statistics on steroids, using machine learning to find patterns a human could never see.
And the applications.
They're so powerful. Identifying very specific sales leads by analyzing past records to see who is most likely to convert. Or building sophisticated models to understand why customers are leaving so you can try to reduce that churn.
So what does this all mean for you, for the listener, moving forward? The takeaways seem pretty clear. First, you've got to have data to move past just having an opinion.
Non-negotiable.
Second, to use that data right, you must know the difference between categorical and quantitative data, because that one distinction dictates everything else. If you treat ordinal data like ratio data, your whole strategy is just built on sand.
And finally, know the difference between just describing what already happened, that's descriptive statistics, versus using that information to predict or infer something about the whole population. That's inferential statistics. And that leads us to our final provocative thought. We talked about two very different study designs. That observational study at Walmart, where researchers just recorded what they saw, just passive observation.
Versus that massive controlled experimental study for the Salk vaccine. So if an observational study merely records data without trying to control or influence anything, what fundamental limitations does that lack of control place on the predictions you can make? The next time you see a headline based on a survey, ask yourself, are you reading about an observed correlation or experimentally proven causation? That is the ultimate test of an informed mind. That's a true deep dive. Thanks for joining us. We'll see you next time.